Hello everyone. Today, it's week 7 today, and I'm Karthik Shinoy. I am the TA for this course, so I'll be taking the tutorials on Wednesdays for those who have not attended till now. I'm just preparing MATLAB. So because this week it's quite interesting because it's it's not so I won't be doing too much of analysis this week. It will come in the following weeks of how to design controllers. So as to talk about our journey, journey till now, what we are so first we modeled the system, we did basic signals, Laplace transform, then we modeled the system. Then we discussed about the time response analysis, the step response and things like that, the specifications like overshoot, rise time, settling time, things like that. Then we discussed stability, the very important concept of how to determine stability of closed loop system, or the poles, where should the poles be, and things like relative stability, how far my poles are from being unstable. Then what did we study? So then next we went to frequency domain analysis, so which gave us a new flavor of understanding how systems work. So how you can add up different frequency components, because it's a linear system, and you use Bode plots, Nyquist plots, and polar plots to see how the system reacts to each of the frequency, and how the stability depends on how many times the point -1 was -1, 0 was encircled in the Nyquist plot, and things like that, and how to determine the transfer function from the Bode plots. Okay, the contribution of the poles and the zeros to the phase and the magnitude. Today, what we'll be doing today, so it will be quite interesting, because you would have heard this almost everywhere when when you would have googled about controllers and things like that. So today is one sec, sorry. So today is week 7 lectures, and then we'll be dealing with PID controllers. So you would have come across this, in your basic some projects which you would have done in BTech, or in your, even in schools you would have done, or in daily life. Actually we are doing this even without realizing it. So when we drive a car, for example, we are, our neural network, our brain is programmed to tune the gains automatically once you see a new scenario. So when to stop a car, without overshooting. If there's a red signal, I mean, usually we shouldn't overshoot, but people do that. So you shouldn't. So how do you stop? If you are traveling at say 10 kilometers per hour, it's easy, but if it's say 60, it's not that easy to stop the vehicle if you see a red light suddenly. So yeah, things like that. So yeah, so that's what happens. So we'll for the first half we'll discuss what, addition of poles and zeros, what will they do to the system. We'll look at both how open loop and closed loop poles, a poles added to open loop and the closed loop transfer functions. Then we'll look at what the minimum phase phenomenon is, non-minimum phase phenomenon is, and then we look at the controllers, the proportional, integral and derivative, and the combination of all these. We'll give examples, and then finally go to MATLAB, where we can use some tools in MATLAB to solve, to tune these parameters KPK and KD. Okay, so I'll start off. So first we'll look at addition of poles, because poles and zeros, because essentially PID controllers are addition of poles and zeros, or changing the gain. So changing the gain we already looked at in root locus. So now we look at addition of poles to closed loop transfer functions. Okay, so what happens? Just a second, I think there is a okay. So yeah, So let's say you have a system with the poles, this is the real and the imaginary. Let's say you have a second order system, a general form of, let's say somewhere something like this, and your root locus, okay, one sec, and your root locus would look something like this. Okay, so for the second order system, it's always stable, right? For whatever k you give, it's always stable. If you add a pole, I mean, we look at this in MATLAB also. Let's say you add a pole here. Okay, I'll draw another figure. Okay, just a second. Okay, so I'll add a pole to it, sigma j omega. Okay, so if I add a pole at say A, minus A, okay, I'll use some other color, maybe this. So I added a pole here. Okay, that's a new pole. Then how will my phase portrait look? My phase portrait will actually change, right? Because something like this, then it will go like this, and these two will do something like this. Okay, so you can see addition of a pole to the closed loop system, or the, sorry, this is the open loop system. What we are doing it right now, it's open loop. Just a second. Open loop, okay, because the root locus is drawn with respect to the open loop poles and zeros. So what will happen is the root locus changes and shifts to the right, decreases the stability, right? So it decreases the stability. What about 0? Zeros, the left half zeros to the open loop transfer function. Wait a second. Yeah, so what will that do? Let's say initially it was like that, we have these, okay, and what will that do? So now let's add a 0 here, minus A. So what will it be? So something like, okay, I'll change the color again, one sec. So something like this, correct? What did it do? It made my system no longer oscillatory, right? There won't be any oscillations, because sigma plus j omega, so it doesn't have any real parts for the entire root locus, correct? So it made my system more stable, if you could say, or because more oscillations, and finally it can go to the right half. So it shifted my system dynamics to the left side. Okay, so if you add a 0 here, what happens? Increases the stability, shifts the root locus to left. Okay, so essentially what you saw is, this is a derivative, and A is my derivative, the control gain or the inverse of the control gain for a derivative controller, and this is my, so this is not a pure derivative, because we are again looking at the root locus, so it's proportional plus derivative, because it's a root locus we are looking at, so we can always adjust the gain k also. Okay, so and this is my integral. So I mean, you will all have a doubt, right? Why even use integral if it makes the system more unstable? So the answer through that is so it's not just stability that we want all the time, or fast response. We want steady state behavior to be good. If I command it to go to 1, it should not go to 100. If that happens, if I launch a missile from here, it might land in the sea, where and it's of no use, right? So yeah, so it won't hit the target, or I can't stop at the car problem. If I want to stop here, I might say overshoot, and this is the middle of the road, right? There is no integral action. If there is no integral action, so Instead of stopping here, I'll have a steady state error of this much. This is bad. If it's an autonomous driving car, let's say it overshoots, what will you do? You can't, right? So yeah, okay. So if we looked at that, now we saw what happens when adding zeros to the left half. Now let's add zeros to the right half plane. The system will still be stable, right? I mean, the stability can change, but because of the zero alone, it won't change. The gain, there may be gain, which makes it unstable, but 2 open loop transfer function. So what will that do? Something like sigma g omega 0 here minus a. So there is a region where the system is unstable, right? So I'll show you that. So in this, if there's this region is unstable, this much, okay, but there is a more important phenomenon that happens. So other locus line will be here. So what you will see, maybe in the lectures you would have seen something like let's say you saw the phenomenon of undershoot, right? Because there is a minus 1 by a times the derivative, correct? So something like that entering. So some y of t minus 1 by a times y dot of t, because it's a, it's over there on the right half. So what you will see is, if you command a step input, what it will give is, it will first go in the reverse direction, then go. So this type of behavior, examples I'll give in pitch control of an aeroplane, because if you see, if the pilot commands it to go up, there will be a small dip and then it will go, usually, correct? It won't be straight like this, okay? For an aeroplane with fixed wings, okay, I mean, it's not a quadrotor or things like that, it's just a so pitch control of airplanes, okay. And the second is, it could be policies, government policies, like for example some government introduces a new tax law. It may be bad in the short term, there may be a small dip in the revenue generated or things like that, but later on the economy will grow back to its desired value. So it's usually like that. So we cannot say that initially if the policy is bad or not. After a while only we can say, okay, some policies. And when you cycle, it's very difficult to notice. If you turn your while steering, when you cycle, if you want to go to right, the cycle actually moves to the left a bit and then right. So that's the problem with so if you would have seen some YouTube videos where they drive the cycle reverse, which is very difficult because of this phenomenon, because your brain can't if it turns right, it's and it goes left, it's your brain will get confused, right? So it's there is a non-minimum phase 0 in that also. So cycle steering, okay. So these are the examples which we will look at later also, but first let's look at let's say, okay, we'll look at what the controller does. Before that, let's say you have a plant, you have an output y of t, okay. I am not going to deal with disturbance in this class, or maybe disturbance we will look at certain types of disturbance and noise also later. Then you have a PID, and you have the error. This is the control actuated signal, this is the reference, and this is fed back in negative, okay. So the error is R minus Y, okay. And what PID gives me is, what is U equal to? What is my PID give? Kp times the error plus Ki integral 0 to t, or I'll take tau, e of tau t tau, okay, this will be t, okay, plus kd di de by dt. So how do you implement this in discrete time, because we don't have continuous time computation, all computers are discrete. So what you do is kp e of k, the current. So if you divide the time into pieces, that is discretizing, right? K plus 1, k plus 2, etc. blah blah, okay, plus ki. How is the integration given? It's a summation. It becomes a summation from 0 to the current value. Let's say it's capital K, okay, e of k times some small sampling time, because there's a dt here, right? So you have some small sampling time, plus how do you do the derivative? Kd is its finite difference, the derivative will be the finite difference, e of k minus 1 divided by the same sampling time. So this is your discrete realization. This is what the computers will do, okay. So yeah, this is how the computers will generate a PID controller. So this will be equal to u of k, okay. And the sampling time, if it is fast enough, you can the control law will be smooth, like not smooth, it can act faster basically. So sudden disturbance can also be dealt with if the sampling time is fast, okay. So we won't go into all that now. So yeah, so we'll look at each term, what it does, kp, ki and kd. For that we'll look at an example. Okay, I think the first order example was done in the lectures. So what I will do is I'll take a you have a cart, for example, a mass, okay, there is no friction. Let's say you have a force which is being applied to the cart. What is the dynamics? F equal to ma, right? M x double dot, the position is x, okay, this is the position, this is x, okay. So yeah, so I was just discussing the PID controller. So let's say we have a mass, okay, I think, yeah, mass, and then a force is applied on it. It could be a moving robot or anything, it could be any car, a car for example, it could be anything. So you have this dynamics. So how do you change this? Where F is the input control and X is your output, okay. Output is X, this is input, okay. So how do you do this? So f of s is equal to m s square x of s, and x of s by f of s is 1 by m s square. Let's say there is no friction here, so there won't be a friction term there, it will be a double integrator. This is called a double integrator system, okay. What happens is, okay, so how do so let's say I want to go to 1 meters and stop there. This is my target, I will draw the target. So I want to reach here, so this is my target. So I am starting at 0, I will reach there. So how do I do that? I will give a step input. You can give a the basic one is the step input. So my reference is a step, okay. So my r of t will be a step, so that will be 1 by s, okay, r of s, okay, I will just erase that. R of s will be 1 by s, okay. So now what? Now I need to, so I will just model it as a block diagram. So I have what here, 1 by m s square, the output is x of s, input is my force, the force generated by it could be a motor, it could be anything, a thrust, it could be anything. So then you have the PID controller where so And what does the PID controller need to do? It takes the error which is generated minus plus, okay, and this is my R of S, okay. So okay, I'll just name it Y of S, okay, as the position. So let's just see what happens if I have a proportional controller. So how is my so what is the root locus? I'll just first see the root locus for the proportional. So proportional means Kp by m s square, correct? Let's say for m equal to 1, mass equal to 1. So my poles are both at the origin. This is clearly unstable. Why? So if I'll just plot and show later. So how will my root locus look like? It will look like this, right? So it will just go along the imaginary axis, something like this, okay. So what will happen is it will start oscillating. Why? We can see why it happens. What is the closed loop transfer function? So closed loop Y of S by R of S is equal to Kp by ms square plus Kp. So where are the poles located? S square, okay, sorry, m was equal to 1. So S square is minus Kp, S equal to plus or minus j root Kp. So this will be my oscillating frequency, omega n, correct? So because there is no damping in this, it will keep oscillating. So if I command it to a step input of 1 meter, okay, x of s, x of t and t, what will I get? I will get something like this. It will keep oscillating, okay. That's not what we want basically, because it will keep, you know, going here, coming back, going here, coming back. That's what is going to happen. I'll show you the animation later on which I made. But the problem is, so what do we do with this? We'll add a derivative term. Derivative acts as damping. So a PD controller, okay, PD controller. So what will a PD controller do? Okay, one sec. Okay, what will a PD controller do? It will add Kp plus Kd times S by S square. That is my G of S, okay. So it added a 0 to it, correct? What does a 0 do? Shift my root locus to the left. So I will just draw that. Now I can change the location of 0 by changing Kp and Kd, okay. So yeah, so my poles were here, I added a 0 here. What will it do? So you will see something like this. Where okay, sorry, it won't be like that. I'll just draw it properly. It will give you mostly something like this. One will go to this side and the other one will go the other side, okay. So that is what you are going to see. Now what will happen? You introduce damping. It's no longer on the imaginary axis. You can place your poles here or make it even here. So you can cut off the oscillations, or you know, by increasing the damping. Let's see if there is some steady state error, how the steady state behaves. So G of S is given to a step input. So what do I do? Okay, the Kp, okay, I will change my steady state error. So what's my feedback? R of Y of S by R of S will be equal to Kp plus Kd S divided by S square plus Kds plus Kp, correct? What is my Y of S equal to? R of S is 1 by S because it's a step input. It will be 1 by S times Kp plus Kds divided by S square plus Kds plus Kp, okay. This is equal to, so Y of t as t tends to infinity will be equal to S Y of S, correct, as S tends to 0 . So what is, excuse me, I think my mic got, yeah. So what will this be? limit s tending to, so this s will get cancelled. So what is it? It's 1. Correct? So my y of s goes to 1, y of t goes to 1. That's what we wanted, right? We wanted it to track a step input. So your y of t, how will it look like? T, it will look like, this is my r of t. It will just maybe oscillate a bit and then go, depending on my where my zeros are. Okay. Okay. Just a second. Okay, so yeah, so that's what I don't need an integrator here. Unnecessarily, why add an integrator? Because there are problems if you add integrator. It will lose the stability. It can reduce the stability of the system. It can cause something called as the integral wind-up, which we'll see as an example later, and things like that. Okay, so we'll look at a different system. Okay, so before that, it's a PD controller. So what all can I control? I can just control the speed of the response. Okay, I can't control the how it behaves steady state, because I don't need to here in this case. So I can control the speed of response if I increase. So I can control the speed of response by increasing Kp, and decrease the oscillations by increasing Kd. So this will increase response speed, this will decrease oscillations, okay, make it slower, the system, it will make it slower. Okay, so that's what is happening, but I don't need a Ki, because I've set Ki to 0, because there is no steady state error. I need not put a Ki. Okay, so, and it's obvious why we don't need a Ki, right? It's a double integrator system, it's a type 2 system, so its steady state error with respect to the step input will be 0. Okay, so now we look at another example. So let's say we have a magnetic levitation system. Okay, so what it's going to do? So it will have a electromagnet. Okay, electromagnet. It will have some. It will be connected to some controller, which provides the force, current, which will turn into the force, attractive force. Let's say we have a sphere, a metal sphere of mass m. Okay, that's the magnetic levitation system. So what will we do? The goal is to control this position x. Okay, and the force is the attractive force. So there will be two forces in play here. One is the okay, so I think I should have drawn it the other way. Okay, I'll just draw it the other way. So it's attractive force, right? So I'll have this coil wound here. Okay, and then there is a metallic sphere. This gap is x. It will have its own weight mg. There will be an attractive force F. Okay, so I can model the system, and there will be some air drag here. Okay, so how do I model this system? I can model m x double dot plus bx dot minus mg, because mg is in the other direction, equal to F. Okay, that will be my because force is attractive, right? It's not repulsive, so it's minus mg. So let's take an example. Let's take m equal to 1, b equal to 0.01, so and g equal to 9.8, and yeah, so what will you get? The equation of motion, the transfer function x of s by f of s will be equal to 1 by s square plus 0.01 s minus 9.8. Now this system clearly is unstable, correct? Because there is a negative here, because in open loop it's unstable. So in closed loop, I'll need to find f of s, and f of s will be equal to my kp times error plus ki times integral of error plus kd times the derivative of error. I'll just write E dot. So that's my f of t, right? My force which I am going to give. So error means if I say I want to be at 1 meters, okay, 1 meter, then the error will be 1 minus x or y of t, whatever the output is coming. I'll have a sensor somewhere, okay, to measure the position. Okay, so now let's see how, let's take a proportional controller. Okay, what will my proportional controller do? So I have k p by s square plus g of s is equal to 0.01 s minus 9.8. okay, 01 s. Okay, I'll just write it 1 sec, minus 9.8. now what is it going to do? G of s, let's take the closed loop transfer function. Before drawing the root locus, we will just take the closed loop transfer function, that is g of s by, so the output will be x of s by r of s will be equal to kp by s square plus 0.01 s minus 9.8 plus kp. So what is it going to be? Let's take the Routh-Hurwitz. Okay, s square, s raised to 1, s raised to 0, 1, 0.01, kp minus 9.8, nothing. So this will be kp minus 9.8. So it should be stable for all kp greater than 9.8. Okay. The problem here is what is my steady state value? Okay, so limit t tends to infinity, x of t is the same as limit s tending to 0, s g of s, r of s. So r of s is a step input, so limit, that is limit s tending to 0, g of s, which is equal to kp divided by 9 kp minus 9.8. okay, so if you see here, there will almost surely there will be some steady state error. It will go to this value and not 1, correct? So that's the so it will never go to the desired value. So we'll have to add a integrator. But the problem of with adding an integrator, I'll show you. So wait a minute. So what will happen is, let's say we add an integrator, it will be kp plus ki by s, s square plus 0.1 s minus 9.8. So if you add an integrator, the order of the system will go up by 1. So what we'll get is, what is the closed loop transfer function? So what we'll get is y x of s by r of s will be equal to kp plus ki by s divided by s square plus 0.1 s minus 9.8 plus kp plus ki by s. Now if I multiply by s, kp plus ki, s cube plus 0.1 s square minus 9.8. okay, I'll just take this common, plus kp minus 9.8 s plus ki. Now let's take the Routh-Hurwitz. S cube, s square, s raised to 1, s raised to 0. So 1.1 kp minus 9.8 ki. So this term will be, I'll call it a equal to 0.1 kp minus 0.98 minus ki divided by 0.1. So that is same as kp minus 9.8 minus 10 ki, correct? So that is, okay, maybe I can write it, okay, let's name it as A only. Okay, what will be here? Ki. So it says Ki must be greater than 0. Okay, that's the first condition from this. Okay, second condition is for it to be stable is Kp minus 9.8 minus 10 Ki must be greater than 0. It should not have any sign changes, right? So Kp must be greater than 9.8 plus 10 Ki. So for stability, okay, we are not considering anything else. So if so which means my system is always stable, right? Because Ki is greater than 0, and so if I choose, okay, it's not always stable. What I mean is, if I choose a positive value of Ki, let's say I choose Ki as 0.1. Okay, we'll do this on MATLAB and check. Let Ki be, okay, let Ki be 0.1. Then Kp has to be greater than 9.8 plus 1, which is equal to 10.8. So for Kp less than 10.8, the system will be unstable. That's what this means. So there will be restrictions on Kp once you fix Ki, okay, or the other way. Once you fix Kp, the restrictions will come. Now the thing is, I mean, this will most likely, stabilize the system. But the problem is, sometimes Kp can be really high, okay, to get the desired transient performance. So what do? I'll add a derivative also. This is stable, but transient specifications may not be met. Hence, add a derivative term. Okay, cool. So then we'll add a derivative term. So all my transients and steady state specifications will they'll be met. Okay, we'll see this in MATLAB. Okay, so next, what do you do? Let's look at the motor example maybe. Okay, which example should I choose next? Okay, I'll choose a simple example first of a furnace control. Let's say you have a furnace, okay, basically where you heat things, and you have to melt stuff and things like that. Okay, furnace control. So you have a furnace here, so there will be some temperature which is say y of t in degrees, okay. Then you will have a heating element, correct, that's my actuator, heater. It will be an electrical heating element. It will give me it will give the input power in kilowatts, for example. It will give the power and it will convert to heat. So I have input power in say watts, okay, watts. And there is a PID controller which will control the current through this, okay. Let's say it's amperes, okay, PID. So what is the set point? So I have the reference say in degrees, so the reference should be the same as my output, and this is negative, okay. Okay, so let's say initially I was at let's say my R of t is 1200 degree. It's a step input, okay. I won't write it as u of t, but it's a step input. So let's say currently at the starting state, currently it is equal to 1100 degree, and suddenly at the next instant, the temperature drops to 1000. I need to find the control input. Okay, sorry. So this will be my power. Okay, my control input U. If my values were Kp equal to 5, Ki equal to 0.2, Kd equal to 0.1, and my sampling time we discussed first, right? The sampling time is 0.1 seconds. Okay, so how do I find this? First I will find the error. So error is equal to for the proportional controller, the error will be 1200 minus 1000, correct? It's the, so it will be 1200 minus 1000, because suddenly it changed to 1000, so the computer will read 1000. So, and my reference is 1200, so it's 200. And what my proportional gain will be? Kp times E, that is 5 times 200, that is 1000. Okay, that's my proportional output. So you know how these are connected, right? So there will be error, there will be Kp, it will be added, then there is Ki, integral, then it will be added, then there is Kd and a derivative, it will be added and given. Okay, I was just making sure you know that. So we have to add all three and give. So secondly, the integral, what is integral? Previous is 0, I am starting. So the previous plus error times sampling time, correct? So that is equal to 200 times what will be that? Okay, Ki is also there, so that will be my Ki times 200 times what? Tau is 0.1. So what will that be? 4, correct? It will be equal to 4. Now my Kd, this is the interesting part. So I have a derivative and suddenly it changed. So derivatives pick up sudden changes in the output. So if you have some noise and all, it will amplify them, because noises are high frequency, right? So they will change suddenly. So my derivative will be equal to 0.kd times the error. Error is 1000 minus 1100, because it was a sudden change. So it doesn't matter the reference is constant, because the reference is constant, my derivative only will see this difference, okay, divided by the sampling time. It's a derivative, right? Finite difference. So that is 0.1 into minus 100 divided by 0.1. So it's a large change. So what will be my PID? So controller effort will be I plus U equal to, okay, so that is 1000 plus 4 minus 100, so that is 904. So it will ask the heating element to give or 904 watts, okay, suddenly. So that's how you calculate PID value, I mean the output. Okay, next, what will we do next? Yeah, so next we will do the motor, speed control of a motor, okay, using PID. So the block diagram usually which we draw, 1 JS plus B, okay, sorry, it's draw it properly. So we have the voltage, which is the input, EB back EMF minus, which gives me the current when I pass through the electric circuit, that is R plus LS. Then I have the torque constant, then I have the mechanical side, which gives me the speed, and the speed is related to this by Ke, the back EMF constant. So I am assuming Ke equal to 1, Kt equal to 10, R is equal to, what will I give R? R I will take 1, B is 3. I'm just giving random values, it won't be correct. I mean, in physical reality it may not even make sense, but just just for the problem I'll just give L equal to 1 and G equal to 1. So what is my transfer function? G, so yeah, so my G of S will be equal to 10 by S plus 1 into S plus 3, and my overall transfer function, what will it be? So this, so omega of S by V of S will be equal to 10 by there is k is 1, so it's just a unity feedback. So what will that be? S square plus 4s plus 13, 10 plus 3, 14, 13, correct? So what will be my, so this is my plant, so this is my plant, the omega, and this is my voltage, so that is 10 by S square plus 4s plus 13. Now how do I control this? I'll take a PID to generate the voltage, I'll feed it back, okay, negative, positive, and say I'll have a reference speed of 1500 RPM or in radians per second. It should be in radians per second. So okay, I'll just change that, maybe say 60 radians per second. Okay, that's my W omega reference. Okay, I want my motor to rotate at 60 radians per second. So my PID, I'll check if I can get away with my proportional controller. Can I do that? If I can get away with a proportional controller, it's always good because it's just a gain. So you'll have just to multiply the error with a gain and pass it. So what will my transfer function look like? K 10 kp by S square plus 4s plus 13. So this is a second order system, right? So what will I get? Omega of S by omega reference will be equal to 10 kp divided by S square plus 4s plus 13 plus 10 kp. You can immediately see that limit S tending to 0, this I'll call it omega of S will not be equal to, so wait one second, so omega of S will be equal to limit S tending to 0 S omega ref of S times 10 kp by S square plus 4s plus 13 plus 10 kp. Okay, so that is equal to limit S tending to 0 S times 60 by S, because it's a step input, 10 kp by S square plus 4s plus 13 plus 10 kp. So what is this? This will be 60 into 10 kp by 10 kp plus 13. Now this part is not 1, right? Is not equal to 1. So which means this is not equal to 60. Okay, it will be less than 60 because and this is less than 60. So what you will see is depending on the, okay, so if this is 60, it might be somewhere like this, or depending on the damping it will go like this and come to this. Okay, so but there will be a finite gap here, it won't be not equal to 60. Okay, so I'll have to add an integrator. Okay, so I'll add an integrator to the system, kp plus ki by s. So my forward transfer function will be into 10 kp by s square plus 4s. Okay, there won't be 10 kp here, square plus 4s plus 13. Okay, and what will be my closed loop transfer function? Omega of s by omega reference of s will be equal to kp plus ki by s into 10 divided by s square plus 4s plus 13 plus kp plus ki by s into 10, correct? So then what will I get? That is equal to 10 s kp plus 10 ki divided by s cube plus 4s square plus 10 kp plus 13 s plus 10 ki. Now if you see omega of s, limit s tending to 0, omega f is equal to limit s tending to 0 s omega of s times this entire term p plus 10 ki s cube plus 4s square plus 10 kp plus 13 s plus 10 ki, correct? So what is that? So this is nothing but 60 by s. So that will get cancelled. So what will happen is finally it will be equal to 60. So that is what we wanted. So which means error will be equal to 0. Okay. So that's what we wanted, right? So this is how you control the motor. Usually you don't need a derivative because the system is usually stable, right? Because we already saw the system was stable. But the problem is it had steady state error. Okay. So now we will go to MATLAB maybe to check some fun animations, and if you have any doubts we will come back, and then yeah, I'll just switch it to MATLAB, and then yeah. So I'll just stop sharing from this. Okay. Stop sharing, and I'll share from this. Okay. So it's visible now. Okay, I hope it's visible. So what I'll do is I'll go to MATLAB. Okay, so let's first do the problem where there was a cart moving. So this is 0. I'm not using g in this, that will be in the second problem. So my g of s is 1 by s square. Okay, this is my transfer function. I'll just change the settings so that the font size is better. Home, preferences, font. Okay. Where do I put the font size? Just a second, I'll just change the font size. Fonts, cool. So I'll just increase 36. Okay, I guess it didn't change much, but okay, I think hopefully it's, I don't know why you can't, maybe this changed but the other one didn't change. Okay, let's why is this command window editor debugger, maybe here? No, I think it's not. Yeah, it's okay. Okay, anyways, so this is G. So then what will so yeah, so I'll just show you what will happen if there's no controller. Kp is 1, everything is 0, everything else is 0. So Gc is Kp plus Kd, the controller transfer function is Kp plus Kds plus Kis, and I am taking the closed loop transfer function. Gc into G is my forward path, 1 is the feedback. Okay, so I just gave a step per input, and this is my plotting. So I'll just run this. Just a second. Yeah, if I run this, you'll see. So you'll see this is my target. Okay, so it will just keep oscillating. Okay, so this is what happens because my Kp is 1, you have seen the oscillations, right? It was on the imaginary axis. We can just plot the root locus and see. R locus of GC into G. What will we get? So we got an C. So here all the roots are imaginary for all k. So let's add a small value of damping, let's say 0.2 or 0.1. Then let's see what happens. So this is we have to reach that 1. So will it oscillate and go? Yes, it's getting damped out. See, it will slowly go to that 1. This is the double integrator system, okay? So it will slowly oscillate and go to 1. So you can actually plot the step response, step of t. So if I plot that, you can see slowly oscillating and going to 1. Let's now increase the so let me check where I was on root locus. GC times G. I have added a 0 to the system, right? We had done this. So adding a 0 made it into circular and went it on pushed it towards the left side. So I could have been somewhere here where the oscillations are a lot and things like that. Okay, I'll just increase my damping or change the location of the 0. So if I do that, let's say I am taking 20. Let's see what happens. So in this case, my 0 was s near the. Okay, I think you missed that animation. So if you see here, there is no overshoot. It's slowly, just like how you stop at a signal, right? Just like how you stop at a traffic signal, it just stopped. There was no overshoot. See, I'll just run that again. So it just stopped. This is how you should, properly stop. And there was no steady state error. Why? Because the system was a double integrator system. Now let's look at the second case where my system was a magnetic levitation system. So it had m equal to 1, b equal to 0.1, 0.01 and g equal to, so something like g by b times s minus m times g. M is equal to 1, so m times g. Okay, I'll first add without any just kp equal to 1. Let's see what happens. Okay, I'll maybe change the I'll change this to, let's say minus 1 to 1, 0 to 2, just so that this is t, this is y, this is t, this is w. It will become vertical, just like a magnetic levitation. So it's getting attracted, the ball is getting attracted, but see, it's unstable, right? It's unstable. So because it was just kp equal to 1. Let me increase the value of kp and let's see if it becomes stable. So it comes, oh wait, what just happened? Okay, I'll just plot the step. Okay, so what happens is it went away fast. It's still not stable. So maybe I'll just increase kp. Oh, before that, it's better to plot the root locus. So I'll just plot the root locus. Let's see if it is ever stable. See, it's very so at the gain of, say, it's very, the system is not that stable. It's very highly, the overshoot is 99.6%. So which means it's bad. So what we'll do is we'll add a bit of damping. Let's see where that takes us. We added a bit of damping, just a bit. Okay, thing. So I'll add more damping. Okay, now this looks promising. So okay, it's going, but why is it going there? It's slowing down and going somewhere. So I'll just increase my damping. I'm just arbitrarily increasing. I'm not doing any analysis based on what damping it should be. So this is highly damped now. So maybe I'll not increase this much. I'll just increase to some 50. So you can see this is not going to 1. There is some steady state error here, correct? It's not going to 1. It will stop eventually, but it's not going to 1. So you can see that in step response. Step of t. So you can see here it goes to some other point. It's not 1, correct? But it's stable. It goes to some value. It doesn't blow up. It doesn't go to infinity. So what we'll have to do? We'll have to add a integrator. So I'll add an integrator as a very small value, 0.1. Okay, let's see what happens. See, it stopped perfect. So it will overshoot and maybe come back. Let's see if it comes back. I hope it comes back. Okay, I guess we'll have to increase the ki value. Okay, so what is my step response doing? Okay, it is overshooting and coming back, but it takes a lot of time because the derivative is too high. So what we'll do is I'll increase this to 30 and this to 20. Let's see what happens. Okay, so this looks promising. I'll plot the step. Okay, this looks better. I'll increase my kp to 50. It should come back now. It's still taking a lot of time to come back, right? So maybe if I again plot the step. So this is how you tune PID values, right? So it's slowly coming back after a lot of time. I'll just reduce the derivative. There's some steady state error now, if you see. So I'll increase the ki value. Okay, the steady state error decreases, but the oscillations increase. So I'll just plot this step. It will go some place, but it will take a lot of time. So the thing is, what we can do is, you can just experiment with it. I'll show you how to do it properly. Okay, now the steady state error has decreased. See, but there are oscillations. Now it is perfectly at the at where I want, correct? So if I increase the increase my kd, the derivative gain, what will I get? Perfect, almost perfect. It still oscillates, but it comes back. So it will obviously come back. So, but it will be very slow because of the derivative gain. Okay, so what we'll do is, since now you got an idea of what to do in this, we'll next see how, one sec, there, logging in, it's logged in, okay. Yeah. So what we'll do is, we look at something called the, how to, so there are these apps, PID tuner app. I'll show you how to tune PID using this. So it will take a bit time to load maybe. Yes. So this is app. I can tune my PID values to get the desired response. First I'll choose the type PID. There are so many types of PID, 2 degree of freedom, where I can change how the disturbance also, how it reacts to disturbance also, and time domain. So I have to choose, I have to give a plant to it. I'll import. So what is my plant? The plant which I have in mind is the magnetic levitation. So you saw how difficult it was to tune the PID values. So there are methods like Ziegler, Nicholas and things like that. Okay, so I'll just, okay, I'm not sure why it's, okay, just a second. Oh, I think it was open already. Yeah, it was here. So this is my plant. I'll import it. Okay. Okay, so if you see here, already it has given me a beautiful plot. It goes to 1. So if you see, the KP values are given here. Maybe it's not visible. I'll just, I don't know how to zoom in with this, but yeah, the parameter, maybe I'll show parameters here. So the controller parameters are huge. KP is 256, 496 and 33. But yeah, so now I can change the response time. If I want to make it faster, I'll just slide it. It made the response faster, but my transient behavior is super, it's overshoot. So I'll reduce this to change the robust to make it slower. If I increase, it will increase again. See, so and so if I want to make it slower, it will work like so you can slide it down, or see here there is no steady state error. So you can play around these values and then design to accordingly. You can change all the step response. I can plot the controller effort, that is the u of t. So if I plot that, what will I get? Let's say it's this. Not sure why it's not plotting. Maybe some issue. So okay, maybe some other issue. Okay, never mind. I'm not sure why it's not plotting. It should technically plot. So you can plot reference tracking, things like that, a lot of plots. Okay, so this is the step response. Okay, so you can always choose just a PI controller. Okay, let's choose a PI controller. You can see it's oscillating. So PI controller won't make my system stable. What about PD controller? What does PD do? PD is actually making it stable, but there is a steady state error. It will go to some steady state value. So I'll have to add an integrator. Okay, so that's the problem. Then we'll look at another tool. This is called the RL tool. You can edit the root locus to get the compensator. I can add a pole or a 0 anywhere I want. So I'll show you how to do that. I think it's here. Yeah. So what I'll do is, so in this one you can see the root locus editor is here. I can add poles, I can add zeros, I can add, so these are real and these are complex. I can add that and check the step response. So I will show you how the step response and all varies with adding open loop poles and zeros. Okay, so edit architecture. So there are so many architectures in which you can design the model, the controller in feedback, control in the forward path, so many. So where, okay, I think it's already there. I think it's not being shown. Okay, one sec. Okay, it was already there. Okay, so you see here the plant, the controller, the feedback and the feed forward path. No, I mean not the feed forward, it's the reference gain. So I'll take G, I'll import my G, which is my plant, G, import, okay, and I'll press OK. So there are so many architectures which you can try out. So this is my system. So it has a pole on the right half. So my root locus is pretty bad, So if you see, now let's add a 0 to make it stable. Okay, where will I add a 0? Let's add it here. Okay, so now if you see, okay, maybe I'll give a, okay. So if you see now the system is stable. Why? Because my root locus plot, I can put my zero, so see, you can see from the step response that it is stable, so it goes to 2, correct. But the problem is I don't have a integrator, so I'll add an integrator. Okay, but this made it unstable, so what will I do? I'll change my, okay, so I'll add my 0 closer, okay, closer than the pole, okay. Okay, before that I'll show you how the root locus varies. Okay, maybe I can show you how the root locus varies when there is a when g equal to 1 by s square. Okay, so for that system I'll change and show control system, edit integer. G is nothing but I'll select G, import. Okay, so what is this? So this is my, so you can see all my roots are here, and my root locus, so I can add a integrator, see, so I can add an integrator, so which made it a bit, or add so I can add a differentiator. Okay, I'll just delete the pole and 0 which I just added. See, the system is unstable because I had added an integrator, right? So system is unstable, you can see on the right plot. I'll delete that also. Now the system is it goes to 1, but it's not because my gain values, but if I change that, it can go to unstable. See, it's unstable now. It was a bit towards the right side. So I'll add a pole. I will add a 0 somewhere here. Now you see what happens. It shifted my system to the left half. Now I can change my gain to change the stability. See, it's stable now with no steady state error like we saw. But yeah, so now you know, like adding poles and zeros, what happens to the system. Okay, so yeah, so that's all what I wanted to show you. I think that's it for today. Maybe if you have any questions, you can post it in the forum. Yeah, so that's all for the day. Thank you. I'll stop the recording.